Let's look at our last two examples from section 6.8 on exponential growth and decay. Continuing with decay, we have this fact that living things contain two types of carbon, carbon-12 and carbon-14. And when a person dies, carbon-12 stays constant, but carbon-14 decays, or when a person or any biological life. In fact, carbon-14 is said to have a half-life of 5,730 years. This change in the amount of carbon-14 makes it possible to calculate when an organism died. So example 4, we have traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.6% of the original amount of carbon-14. If the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? So the idea here is they're trying to date these ancient tools, and since they were buried along with some wood, they think if they can carbon date the wood, it will give them an idea of how old the tools are, because the tools are not cannot be use carbon dating on them since they're not an organism. Okay, so the function we'll use is this one. Okay, so we don't know K, but we know the half-life. So we'll start by find K using half-life. We know that we have 1/2 of the original amount when T is 5,730. Divide both sides by a sub 0 and solve for K. Change this to a log. The base is E. So K is the natural log of 1/2 divided by 5,730. Again, I don't want an approximation for that. I'm going to use this exact value. Part 2. So here's the final step. Find T when A of T is equal to, so they're saying at this point in time, the amount we have is 0.0167 times A of 0. That's the percent we have left. Okay, so when we have 1.67% of the original amount, what is T? So plugging 0.0167 A sub 0 in for A of T. So see, it doesn't matter how much you start with. K is the natural log of 1/2 divided by 5,730 times T. We'll divide both sides by A sub 0. So we have natural log of 1/2, 5,730 T. Okay, we have an exponential, change it to a log. So here's our exponent, the natural log of 1/2 over 5,730 times T equals log base E of 0.0167. Okay, so T is equal to, I'm going to multiply by the reciprocal, 5,730 times the natural log of 0.0167 divided by the natural log of 1/2. Just took this fraction, flipped it, right? Multiplied. That's a calculator problem. I got what? 33,829.9, or I'm just going to say approximately 33,830 years ago. That's when the tree would have burned, and perhaps then they can say that's how old these tools are. Okay, let's look at the last example. The half-life of cesium-137 is 30 years. So it takes 30 years to go from how much you have now to half of that amount. If 25 grams is present now, how much will be present in 10 years? So our K. We're going to find K using half-life. We know that we have 1/2 of the original amount when T is 30. Divide both sides by A sub 0. Change it to a log. Y equals log base E of 1/2. So K is the natural log of 1/2 divided by 30. Now we need to find, it says how much will be present in 10 years. A of 10. A of 10 equals, we have 25 present now, times E to the K is natural log of 1/2 divided by 30. T is 10. So that's my whole exponent on E. Just run that through your calculator, and I got 19.8, and this was in grams. And note that most of the radioactive materials that were released from the Fukushima plant after that 6.8 magnitude earthquake in 2011, you might remember that in Japan, most of that was cesium-131 or cesium-137, I mean, and iodine-131. So this is something that actually happened and got out into the environment, and it was of great interest to scientists to figure out how long it was going to hang around.